Good evening, everyone. We're going to get started. I'm Deborah Davidson, the founder and director of Catalyst Conversations, and I'm so happy to welcome you to this Catalyst Conversation. And I want to thank the LIST Visual Arts Center for hosting and presenting this program with us. And I especially want to thank Paul Ha and Emily Garner for their continued generosity. Thanks to the Cambridge Art Council, our founding partner, our board, and all our volunteers who help us out, and to those of you who have donated recently. Catalyst was founded to open a critical path for dialogue between the arts and sciences. We present intimate and provocative conversations between artists, scientists, and the public. We're interested in connecting the two through programs, educational outreach, and public events like this, which demonstrate the important conversation and synergy between art, science, and technology. This evening's topic is Atoms, Geometry, Algorithms, with Tess, Smidt, and Erik Demaine. They share a relationship to both science and art. Their passion for what they do is guided by their openness to working across the sometimes borders between science and art. We're going to begin with introductions by each of the speakers. They then will share with each other and me their respective thoughts on the relationship between art and science, their response to each other, and the parallels and importance of iteration in their respective projects. Tess Smidt is an assistant professor of electrical engineering and computer science at MIT. She earned her SB in physics from MIT in 2012 and her PhD in physics from the University of California, Berkeley in 2018. Her research focuses on machine learning that incorporates physical and geometric constraints with applications to material design. Prior to joining MIT, she was the 2018 Alvarez postdoctoral fellow in computing sciences at Lawrence Berkeley National Laboratory and a software engineer intern on the Google Accelerated Science teams, where she developed Euclidean symmetry equivariant neural networks which naturally handle 3D geometry and geometric tensor data, and she will elucidate that soon. Erik Demaine is a professor in computer science at MIT. His research interests range throughout algorithms, from data structures for improving web searches to the geometry of understanding how proteins fold to the computational difficulty of playing games. He received a MacArthur Fellowship as a computational geometer tackling and solving difficult problems related to folding and bending, moving readily between the theoretical and playful, with a keen eye to the revealing the former in the latter. He appears in the origami documentaries Between the Folds and Nova's The Origami Revolution. He co-wrote a book about the theory of folding, geometric folding algorithms, and a book about the computational complexity of games, puzzles, and computation. His interests span the connections between mathematics and art, including curved frieze sculptures in the permanent collections of the Museum of Modern Art in New York and the Renwick Gallery in the Smithsonian. So with that, Tess will begin, followed by Erik, followed by conversation.
Thank you so much for the introduction and also for making this happen. I'm thrilled to be here. It's a pleasure to meet all of you. And today I'm excited to share, let's see, on button. Okay, great. So today I'd like to share with you a bit about atomic architecture, at least some aspects of it. So designing atomic structures and also taking inspiration from them. So my talk will have two parts to it. So first I'm going to talk about basically how do we go from atomic structures, basically where are the atoms, to figuring out their properties, what are they doing and how might we find them useful. And then I'm going to talk about how do we generate new arrangements of atoms based on things that we've already seen. So first let me introduce you to some atoms. So just as written language is not random combinations of letters, spaces, and punctuation, atoms don't form random arrangements. They form recurring patterns that can occur at many length scales. So here's three representative cases of different ways that atoms can connect up to form different structures. We have a humble aspirin molecule, which you may have encountered for headaches. There's a silicon crystal. You take this box, you have atoms in the box, and you tile that box everywhere in 3D space, and you have a crystal. And this silicon crystal you'll find in pretty much every single electronic you've ever interacted with. This is what it looks like if you zoom in. Last but not least, we have a hemoglobin protein, which allows us to breathe, thank goodness. And it has many different complex features. It has iron in these little molecular complexes, and it also has these lovely alpha helices that are basically formed by different amino acids, another type of molecule, making these nice little helices. So as you can see, there's a lot of beautiful patterns in these structures, and so we'll talk a little bit more about them. And in the rest of the talk, I'm going to be focusing more on this silicon crystal, or not the silicon crystal specifically, but crystals in general, because they particularly have some very symmetric patterns. All right, so we've talked about structures. What do I mean by properties? So properties is a very general term. It literally means like any way that a structure interacts with or affects the world. And that can be many different things depending on what the molecule, material, or protein in question is. Here are some examples. These properties can be as simple as, is this assembly of atoms stable, or do the laws of physics force them to fly apart from each other? To things like, is this molecule toxic to birds, or is it harmful to the environment? Or do different molecules want to bind to this protein? So these are all properties. So given an arrangement of atoms, in many cases, we can actually calculate their properties using existing computational tools. And this is a pretty amazing fact. This is a feat of many, many years of science and engineering. So if I take my silicon crystal structure, this is the same one you saw before, just a different way of expressing it. And I use quantum theory and supercomputers, fancy stuff. I can get some of its properties, which in this case are, where are the electrons and what are they doing? And using that information, I can figure out, would this make for a good photovoltaic to capture energy from sunlight? Would it be good for quantum computing to do interesting quantum algorithms? Or might it be helpful for various types of energy storage materials, such as batteries? The issue here is, while we are able to do this, it's very computationally expensive. I said supercomputers, and in case that you've never worked with supercomputers before, this is one row of, I think, 10 or 20 rows of cabinets of computers of the Cori supercomputer at Berkeley National Lab. And so this is the machine, these are the types of machines that we need to use in order to get these insights. So pretty computationally expensive, lots of energy to run these calculations. Okay, so there might be a fix to this. We can actually emulate these computationally expensive calculations with much faster machine learning methods. But there's a problem. We as scientists want certain guarantees that if we're going to apply machine learning to these quantum mechanical calculations, we want to make sure that it's going to be able to use our relatively limited data. It's very expensive to generate our data. We have to use the supercomputer, so we want to make sure that it gets it right. So one important way that we describe physical systems to computers is that we use coordinate systems. So if I have this assembly of molecules, and I want to tell the computer where these molecules are, I would use a coordinate system. So I'd say, okay, well, this atom is this far away from the origin along the X, Y, and Z direction. But I could have just as easily chosen another coordinate system, like coordinate system 2. It's representing the same thing, but the numbers written down will look completely different. Our simulations can handle this no problem because it's doing the computation from scratch. But for traditional machine learning methods that you grab off the shelf, they see 1 and 2 as completely different, and there's absolutely no guarantee that it's going to give an answer that's even closely related. So this is problematic. So what we would like is we would like methods that understand that system, or the system described by coordinate system 1 and coordinate system 2 are describing the same thing just differently. Another way of saying this is that we need a method that can handle the symmetries of our coordinate system. So this is what I do, and my graduate students who are appearing in the front row. So we build machine learning methods that have symmetry baked into them. not only is this super helpful for handling the conundrum of arbitrary coordinate systems, but it's also useful because properties of symmetric systems are also symmetric. So this is the graphic that you may have seen on the poster, so I'll kind of explain it now. So if I take 3 random copies of these models that we make, they haven't been trained on anything. They've just been, initialized in the ether. And I ask them to make a shape given an input, and I give as input these very symmetric, very lovely shapes, a tetrahedron or an octahedron. These are just kind of 3D polyhedra. That's the 3D version of a polygon. And so if I give them this as input, these are the shapes they make. It's kind of cool. It's kind of like this is their interpretation of a tetrahedron and octahedron. So they're lovely objects. And importantly, they look similar in certain ways to the tetrahedron and octahedron. If I rotate this tetrahedron by 120 degrees, it looks the same. If I rotate this object by 120 degrees, it looks the same. Another way of saying this is that they have the same symmetry. So these methods don't have to learn about rotations, and this allows them to focus on the hard stuff, which is learning quantum mechanics, like learning how the electrons in a water molecule interact. Here's my water molecule. Here is a matrix representation of how those electrons interact in the water molecule. What you'll notice is that this is rotating, but I trained this model just on one of these rotations and one of the rotations of this complex geometric tensor. But as you can see, it's able to make a prediction that I can assure you is correct for that water molecule. So it only has to see one of these examples to predict something that actually changes in very complex ways. But what's even cooler about this is that if you remember the mentioning of supercomputer calculations, so even with a machine or a computational machine that size, we can only really feasibly do tens to hundreds of atoms at a time. And the world has more than 100 atoms, so there's certain things that we can't quite calculate. But with these methods, because they're so much faster, we can now tackle hundreds of millions of atoms. And this is a picture of what 100 million atoms might look like. You have to zoom in. This is 50 nanometers, so it's still pretty small, but we're getting there. You can't really quite see, but these individual dots are atoms. So we can tackle problems that we fundamentally could not do before. It literally would have taken the age of the universe to try and compute this. But now it only takes a few seconds. So that's pretty fun. Okay, so that was structures to properties. Now let's talk a little bit about structures. So ultimately, quantum mechanics is our design critic. It's what tells us whether a structure is good or not, valid or not. But that shouldn't constrain our design process. We still have kind of creative license to find structures in any way we would like. So we can kind of draw from the design principles that other fields have leveraged for designing buildings or industrial art. So we can leverage these for designing atomic structures as well. And another thing is that geometry is universal, so anything we find could also be useful elsewhere. So can we infer new geometries that are implied by the atomic structures we've already seen? And might these geometries be helpful at other length scales? And so I'm going to give 2 examples from my own personal research. This lovely structure is mithrene. You might be wondering, why is it called mithrene? And that's because silver benzene selenolate is a mouthful. Also, this crystal structure glows blue, like the sword Sting from Lord of the Rings, which was made by the elves, and the elves also made mithril. So mithril, mithrene. Turns out the chemist is a Lord of the Rings nerd. What I love about this structure is this kind of 2D layer of tetrahedra that are sharing edges, which is right here and right here and right here. These are all just different views of the same thing. And so I decided to make a model, and out of paper and tape, not nearly as pretty as the paper models that you're going to see later in Erik's talk. But what you'll notice is that these edge-sharing tetrahedra are actually quite dynamic. They actually will collapse into these curved forms. And turns out, if you make this same model out of fabric, it makes an excellent pillow to decorate your house, great support for the neck, also a great cup holder for when you're doing research on the couch during the pandemic. But making models can be a little slow. And so I went ahead and also made a computer model using rhinoceros and grasshopper. These are tools traditionally used by architects to explore different forms. And I use this to kind of just explore what are different ways that these tetrahedra can kind of come together and form shapes. And for a certain number or certain ways of parameters, you can actually kind of coerce this shape into forming these nanotubes with bond lengths and angles that are actually chemically pretty reasonable. So we've yet to make this, but it's definitely on our list. My synthetic chemist collaborator and I, we're maybe going to try this later this year. There's some other things in the pipeline. But this is something that we're excited to see if we can actually stabilize by choosing some organic molecules that would help stabilize this structure. All right, here's case study number 2. This is lithium iridate. And lithium iridate has these beautiful octahedral patterns that can hook up in 2 different ways. So either they hook up through the edges of the octahedra to form something that spans the same plane, so it's a flat structure, or they can hook up in a way such that this part and this part are in different planes. And depending on how you stack things that are in the same plane and different planes, you actually can form an infinite series of given crystal structures, of which this one, and this one have been synthesized. But the story doesn't stop there. These octahedra are not actually perfect. They're slightly distorted. So if you take an individual octahedron and you take these opposite faces of the octahedron and twist them in opposition to each other, that's actually what the structure is really doing. And I became curious as to what would happen if you take that distortion and go all the way, such that you distort the octahedra into this trigonal prism. So if you take all the same plane bonds, you can make a tiling structure that expands and contracts. Kind of cool. You could imagine that, maybe you make a screen and it pops out, or, maybe it'll have some interesting electronic property. What's even cooler is if you take the bond that changes planes, you'll see it goes between being a 3D structure that kind of pops out to being a 2D structure that lies flat. Now for this one, making the computer models was really fun, but I wanted to see how would you actually go about making a physical model of this, because this is a bit harder than the tetrahedra, because the individual unit is now changing. Well, it's still a work in progress. I've tried a few different things. My first attempt was making this 3D printed piece, which actually works pretty well. We just need to find a way to print a bunch of these in connection to each other. And then more recently, I've been hanging out a lot in the M.I.T hobby shop, which is just about the happiest place on earth. Hi, Kobe. And I've been learning to do some metal fabrication and welding. And so this is a kind of overly complicated linkage that is able to accomplish the same thing. What this makes me realize is, man, electrons are really good at making complicated distortions. So in general, tinkering helps me kind of explore and think about new ways to use geometry or just get new perspectives on it. And in general, outside of research, I like to make objects that kind of surprise and delight folks as to how they might kind of do something that maybe you didn't think that they should do. So one of them is something that I made when I was an undergrad with 3 of my fellow undergraduate classmates. And these are the Cosmic Ray Chandeliers. One of them is still in operation. One of them went on the fritz a couple years ago. These are chandeliers that light up when they detect cosmic ray muons, which are particles that are created when particles from outer space come colliding with the Earth's atmosphere. And then it creates a shower of these particles, such as these cosmic ray muons, and they light up. So you may not have realized, but this is happening around you all the time, and so these chandeliers shed light on that. And then more recently, I became an assistant professor here, and I needed a desk. So why buy something when you can make something? And with a lot of help from the instructors at the hobby shop, I arrived at this design and was able to make this lasagna noodle desk, which is made of maple. Fun fact, the top parts and some of the other straight pieces are actually made from maple that Kobe reclaimed from the M.I.T basketball court when it was being redone. So that we got a little bit of M.I.T in the desk. With that being said, I want to give a big shout out to a lot of my collaborators and fellow mischief makers, because science and making things is much more fun with friends. And I'll leave you with these takeaways and any questions, I guess, or I guess maybe we'll later questions. Yes. So yeah.
Nice.
Thanks, Erik. All right, you're up.
So finally, I get to see you give a talk.
I know.
So I'm Erik Demaine, and I can make this. I am a computer scientist here, but I also do art, and I want to tell you about two different contexts where we like to explore art and science together. One of them is paper folding, origami, and the other is glass, and sometimes the two together. But I also wanted to give you a little background, sort of how we got here. So this maybe is less happy, or did you turn it off? No? Yeah, all right. Oh, yeah, okay. So I work a lot with my father, Martin Demaine. I know it looks like me, but that's my dad in the 60s, I think, 1972. He was the father of Canadian glass blowing. And so this is all before I was born. He made all sorts of cool glass sculptures. So his background is in art. And then we started collaborating together when I was 6. That's me in the bottom. And we made these wire take-apart puzzles and sold them to toy stores across Canada. Split the money 50-50. And then he homeschooled me from ages 7 to 11, I think. And so that was a big bonding experience, lots of traveling and experiences together. And so we became really close collaborators through all of this. Then I went to university and started doing computer science and math, and I taught him computer science and math. And then he taught me art, and we do both together. So we've written hundreds of math papers together, and we've made hundreds of sculptures together. This is an example of glass and paper together. And yeah, now I blow glass too at M.I.T. So let me tell you about paper folding first, and then we'll go to glass blowing. So here's an example of a mathematical or algorithmic result in the theory of paper folding that you can sort of make anything you want. So you take as input this three-dimensional polyhedron, whatever you want to build. And this algorithm called origamizer translates it into a crease pattern. You fold the solid lines mountain and the dashed lines valley. It takes only about 10 hours, and you get your bunny all folded. So here's an example of that, a similar crease pattern folded out of a sheet of steel. So the idea is you can take any sheet material that can hold a crease and fold it into any 3D structure you want. This is like 3D printing, but for hollow, thin, lightweight structures. Oh, I don't want music. And this is the steel bunny. So you can think of this as a manufacturing process. There's lots of applications here. We also make software to try to simulate paper folding. This is a free one you can play with online called Origami Simulator. And so you don't even need to get out your piece of paper and fold these, I don't know, it's probably about 5,000 creases or so. And instead, it's a lot easier, especially for checking that we designed something correctly. On the application side, our original goal was to make cooler artistic origami. And there's been a huge surge in the last few decades on complex origami. But then on the engineering and science side, whenever you want a deployable structure, something that can be big and temporarily fold small, like a telescope lens you want to deploy into space, or a stent you want to put inside your body, or an airbag that you want to store inside your steering wheel, these are all origami folding problems. And a lot of these are being studied actively in this community. Or in the top left is a folded Kevlar. So you have a deployable shield for the coming apocalypse. Bulletproof. This is a dress that's been 3D printed in folded form, so you can use a much smaller and cheaper 3D printer. And this is a shoe sole, which is competitive with the best foams in the market for running shoes. So all of these are folded sheets. And there's a growing literature in self-folding. where you don't even need the origamist to fold the sheet. All the things I've shown you pretty much have been folded by hand. These are all sheets that fold themselves. And this is particularly exciting in the top right, making self-folding robots. So you just use a laser cutter and laminate a few sheets together, add a couple batteries, and the robot folds itself into its 3D form and starts working with no user doing the folding. So in a couple seconds, it should walk away. Cool. So this is a particular, how did we go from origami to art? I mean, obviously that was one of the motivations, but my dad and I got really interested in this model called the hyperbolic paraboloid. You take a square, you fold concentric squares and a diagonal, and we folded thousands of these, but it turns out they don't exist mathematically. So this is a fun example of building something in real life that can't possibly exist. So we also get the reverse sometimes, but like some of the really complicated foldings. The paper is cheating somehow in a way that is not allowed mathematically. It's probably stretching or adding extra creases. Then we moved to a similar form, but with concentric circles instead of squares. And this we think exists. We're close to a proof, but we've been close to a proof for several years, so it's still unsolved. These are the pieces at MoMA, some of our first explorations. And then we've been exploring taking many of these circular parts and composing them together. So here's a little video of what it looks like to put them together. So each piece wants to be in a nice equilibrium form, but they're willing to conform to somewhat to what we ask them to do and fit together. But there's a fun kind of back and forth with the material wanting to fold one way and us wanting it to be symmetric and things like that. And we've been exploring making these pieces larger and larger. This is us in my dad's office over in the Stata Center. And on the art side, we've been playing a lot lately with printing content onto the piece before folding it. So this is the first piece we did of this flavor is based on this short story called The Destructors, which is what they're reading in Donnie Darko. And the theme is destruction is a form of creation. So we took that as permission to fold this story into a sculpture. And if you destroy the sculpture, you can unfold it and read the text again. This is an example with some mathematics. So there's QR codes, you may not know, use an error correcting code. So you can cut a huge circle out of the middle of a high quality error correcting code, and this will still scan. It says folding error in prediction of what's going to happen. Do not scan the upper ones. It doesn't work so well. This is a hypothetical collaboration with Joseph Albers from the Bauhaus, because he or his students actually folded some similar sculptures to these with curved creases. And he also designed this mural in the top left called Manhattan. It's like towers in the city or tall buildings. And so we reimagined this in a circular form and kind of, he's dead now, of course, but we imagined a collaboration with him folding these forms with his patterns. This is a piece of the entire collected works of Shakespeare, restricted to just the words that contain red. So just the red words, there are 235 of them, and they look pretty cool. And this is a recent piece of Beethoven's hand-drawn scores folded into a musical mess. And through all this, we're making sculpture, and I'm showing mostly sculpture here because it's much more visual and easy to see cool things. But while we're exploring these, getting intuition for how curved creases work, we've also been developing a series of math papers that prove exactly what does work and what is possible through curved creases. And so we can characterize which things are valid and use that mathematics to analyze sculpture as well. So these are some sculptures by David Huffman, who was an MIT student and professor back in the day. And he moved to the West Coast in the 70s and started doing these curved crease foldings. And we can analyze them computationally and mathematically and prove that they actually work. Or in some cases, they don't work the way we thought they did or the way he thought they did. This is a very cool model of a column. And we thought the pattern was the thing in the top left, but it's actually, that's impossible. And it's probably something more like this, but still ongoing. Or we can use this idea to design new art pieces. So this is a folding of a Picasso one-line drawing out of one really long wiggly strip of paper. So unfolded, it looks like this, and folded, it looks like the Picasso dancer. Okay, glass next. So let's start with sculpture, and then we'll go back to science. Because my dad's a glass blower, and then I learned to blow glass shortly after we moved to MIT, we wanted to combine paper folding with glass blowing. And the first obvious way was to use glass as a vessel for the paper. These are like ships in a bottle. The puzzle is how the paper get in there. With printed patterns, here we have the pattern of a sunflower, and the glass also has a little flower on it. Another way to combine paper and glass is to pour hot glass onto paper. Another obvious way, I guess I should say. So this is hot glass fresh out of the furnace, over 2,000 degrees Fahrenheit. And if the paper is wet, you don't burn all the way through, and you get a really nice char pattern. And so we make these kinds of pyro prints and then fold them into paper and then insert the paper into glass. So we go full circle from glass to paper to glass. We've also tried folding glass directly. This is joint work with Peter Hauck, who runs the glass lab here at MIT. It's actually quite tricky to get to get glass to fold like paper. I've never thought about getting paper to fold like glass. I think that's also very tricky. But we have, one of the more successful ways is to use a mold and press hot glass into this like zigzag folding. And that lets us get a kind of pleat folding. Or we also explored making these curved crease sculptures out of glass. This is a lot harder. And it's made with a technique called glass cane, where you take long, thin cylinders, which is the next topic. So this is an example of cane. You've probably seen cool glass art like this. This is a piece by Lino Tagliapietra, who's the best glass blower in the world, made here at MIT when he visited. He used to visit a lot. It's been a while. And these are sort of the standard Venetian glass cane patterns. But we wanted to design new ones. And so we made software, computer-aided design tool called Virtual Glass. It's also free online. And you can design your own cane in cross-section and see what will happen if you pulled and twisted this pattern of color. And then also see what those canes would look like on a finished vessel. And so we used that software to design new glass canes and then make them. In this case, the Museum of Glass in Washington State made them. And yeah, you get some pretty cool new things. And the idea is to predict what these will look like ahead of time so you know whether they're worth making. Because a lot of glass cane patterns are very hard to make, and they end up looking pretty much like other ones. So we really wanted to get something new. And my very last topic is another fun medium where art and mathematics come together for us, which is font design. My dad and I just love fonts. We think they're cool. And we use fonts as a way to express mathematics and also puzzles embedded inside. And these were recently featured in the New York Times. So here's an example of a glass cane font. These look like letters. These are cross-sections of cane. If you pull and twist them, you get some pretty cool shapes. And the puzzle is, if I just gave you this side view, could you figure out what the cross-section is? And with a little practice, it's possible. And this is a physical font that we made out of hot glass in trying to think about how to actually simulate glass forming, glass working on a computer. This is sort of making art to help us figure out what the right computer model would be. This is a font designed around the one crease idea I showed you. So this one strip folds into a letter B, and there's a whole alphabet here, so you could string all the letters together. And this is a crease pattern, and a few thousand creases up there. Blue lines are one way, red lines are the other. You fold it, you get the 3D structure of the word science. And there's little gray patterns at the top, and they come together to form this false shadow of art hiding in the background. So just to give you a little flavor. In general, these are the talking points for later. My dad and I like to think of art and design and math and science as all kind of like one thing. It's just like making stuff, coming up with stuff, inventing stuff. And it's all about the creativity and the problem solving that happens. It's just, science and math have very rigid constraints in what makes a valid math paper. But all disciplines of art have hard constraints on what's actually makeable. And for us, a big way to access this world is through collaboration, in particular with each other, but also with other people. And that's a really powerful way, especially to cross over disciplines and learn new things. So that's it for me.
Those were both terrific, and thank you. So maybe we'll just start the conversation by something that I have been thinking about, kind of relates to what you were talking about, Erik. So I'll just read it, and then you can respond. So I wrote that an example, among many other things, of the synergy between art and science is the importance of observing. So nothing that either of you talked about, but that you obviously do. The underlying powerful idea is that of curiosity, which is fueled by inquiry, which is fueled by careful observation. Once you start looking and paying attention to what you are seeing, the world changes, i.e. your perception of the world changes. That increased perception leads to a better understanding of it. This is essential for both scientists and artists. By paying attention, artists and scientists alert all of us to do the same. So that's just something I think about a lot. And the other thing, and we had talked about this when we met several weeks ago, is the importance of the physical hand, of making with your hands. And I think for you, Tess, you said, like, I loved your little, tetrahedron, your pillow thing, and that you're anticipating actually making something by hand soon or in the future, and that's really an important aspect. And I think you didn't show the video of you making the desk, but that was a
that would have been a 9-month video.
But it demonstrated your. It's not just like I'm good, like your need for using your hands.
Yeah.
And Erik, I think for both glass blowing and the folding, which are very hand intensive, but the use of the hands feeds the intellectual or the scientific. This is what the algorithms do. So you are both in both camps, which I find really interesting. So.
Yeah, I mean, for me, I got started in this whole thing because we just needed physical models for what the heck we were studying. We needed something that we could manipulate. I'm guessing it's the same for you.
Yeah,
that
totally.
Computer models, cool, and you see a lot, but you get a much more visual sense holding it in your hands and being able to manipulate it, especially for something that's reconfigurable. Yeah. And but once you're making models, then you start to deal with all the real-world physical constraints, and then you can embrace that and turn them into something cool, like a pillow or sculpture.
Yeah, I think also making something real allows it to sort of surprise you. At some level, a computer model can only do what you told it to do. I mean, and sometimes not. I've also made some computer models, like our neural networks have often corrected me. I'm like, no, that's not symmetry preserving, I'm sorry. So sometimes computer models do talk back, but it's so much easier and also it's so much more immersive to kind of feel the resistance of something, to engage with an actual medium to observe. In order to observe something, something has to be there, and computer models are one way, but working with different materials and different settings, and even just changing the length scale. I unfortunately can't go in and really, put atoms exactly where I want them. I mean, sometimes you can, but it's harder. So it's really useful.
I thought it was funny when you said, it'd take longer than the lifetime of the universe to simulate this physical system. I was like, wait a minute. If you could just build the physical system, you could see what happens with physics.
That's right, yeah.
But building the physical system is the hard part there.
Yeah, synthesis is really a challenge when it comes to atomistic structures. So for organic molecules, we often know how to make them. But for different types of crystals, I can propose for you a crystal, but being able to make it is very challenging. We
That's
don't
why-
know. Yeah.
That's why you're the atomic architect, not the atomic structural engineer. Or
That's
something.
right. Yeah, that's right.
Right.
My collaborators are the structural engineers.
Right.
I subcontract that out.
I do like computer models too. I'm a computer scientist, I have to. But my dad's favorite moments with computer models are when there's a bug in the program, and it renders something completely unrelated to what we were trying to make, and it usually looks cooler than what we were trying to make.
Yeah.
It's like, oh, save that! I don't want to lose the buggy version of the software.
Yeah. I mean, that's the experience often of an artist, where it's like
Right.
the thing that you're working on then starts not talking, but reflecting back, and you see something that you didn't or you couldn't until it was there to see. So there's that again, that kind of not just observation, but like really deep observation, which leads to perception, which leads to ideas, right? So
Yeah, that's a lot of fun when the material talks back to you and doesn't want to do what you
right.
thought it was going to do, and
Yes.
then you can embrace that and
Yeah.
see where it takes you.
Yeah, that feedback that you actually get from interacting with a system
Yeah.
that you're just able to kind of be with in the moment rather than, though you can do this in ways with code, but it doesn't feel as streamlined. That's why interactive environments like Grasshopper and Reiner are so helpful, because you can just immediately see what your algorithm is generating in a live feedback sort of way. So it's observation is so important, but you need something to engage with to observe. So tools are really important for that.
This is just kind of an aside question, but do you find with your younger students who have maybe less acuity with their hands, or who use their hands less in terms of being educated, that this is challenging? Like you have to teach them about using their hands? I'm just curious if that's an issue or not.
I've definitely, I tell them a lot about my experience, my personal experiences in the hobby shop and how much joy that brings me to making with my hands. And I think, some of my students come with varying levels of tinkering. And so I think just me saying that it's a fun thing to do encourages them to go try it out. But time will tell as to how that goes, since I'm just starting out.
Right.
I definitely encourage students who take my graduate classes on folding and whatnot. One of the options for projects is to make art and sculpture. Surprisingly few actually do it. I think a lot of them appreciate it, but I think it's a little scary maybe to enter. So I haven't had as much success as I would like in corrupting young minds. On that side, I corrupt them on the computer science side a lot.
I'm looking at my list here.
Yeah, no,
Oh, yes. I made a list. I'm not going to read it, but it kind of is like a poem based on our conversation. We were talking about the unknown and taking risks and machine learning. So I don't know. Maybe we could. I'm just going to throw out the first one, the unknown. So how does that motivate you? You're trying to find something that is unknown, right?
Yeah.
You're going to know it by looking for it, right?
yeah. I guess that's kind of the definition of research. And also I think of just the creative process is, sometimes you have an intent like, oh, we're going to try and make a thing that does this. Sometimes you have a goal, but you often find you need to abandon the goal because you observed something or you found something or something.
You don't formulate a hypothesis before you formulate the experiment? No one does.
Just more like, well, I'm going to go in there and I'm going to poke the system this way, but I don't know what's going to happen after that.
Yeah, that's good. Yeah, and not to be kind of courageous.
Yeah.
To being able to do that, because not everybody can or wants to do that. I think, and it's clear in both your projects, and that motivates. That's going to motivate you your whole life.
Yeah.
It doesn't go away.
Yeah, I think the unknown is really exciting, exactly because you don't know what's going to happen. It really feeds into the curiosity side. I feel like one of the problems with most schooling is that it's all about teaching things that we already know instead of encouraging you to explore things that no one knows. Maybe in a good school they'll let you explore things that I know but I won't tell you. And you can discover it for yourself, and that's useful. But I think
so that's
pushing the envelope of what the whole world knows is much more exciting than just figuring something out for yourself.
Yeah. I find projects being like just having kind of a goal in mind of wanting to make a thing or try to attempt a thing, and then figuring out what tools you need to recruit in order to go from an idea to reality. Like just that entire process is such a rich learning experience, and there are many unknowns in there. You have to be bold enough to say like, I'm gonna make a desk that looks like a lasagna
Exactly.
noodle, and then be like, great, how do we do that?
Exactly.
That was
right.
I learned so much
let-
just by committing to a very unreasonable design.
Right. Well, maybe that's your architecture background, right? Because architects do that.
They're very unreasonable. It's
Unreasonable,
fantastic.
Right. I mean, we have a couple of examples on the MIT campus of
That's
those
right.
kinds of projects.
Yes.
Yeah.
And I'm glad
That
they
leak
exist.
and things like
a,
that, right?
Or a perfect spherical dome.
Right.
It's no longer spherical.
Yeah.
The other thing we were talking about was metaphor. And people who have been to programs before have heard me say this, but if you'll indulge me, and maybe you can respond to it. So it's something that Alan Lightman said to me, the physicist and novelist who is here at MIT. And this was actually before Catalyst was anything. It was like an unborn baby. And I went to him for just advice, and do you think this is a good idea, and so on. And he said something like that both science and art live in metaphor as they begin. And eventually, science has to leave the metaphor and start, iterating and repeating itself. And that the art can can continue in the metaphor. So it seems perhaps that what you've been talking about is this relationship between art and science, is that we're sort of playing in that space, that overlapping space where the metaphor exists, so our brains can understand a little bit, but art, you can keep staying in that kind of imaginary space, I guess. So, any thoughts?
I guess you could, but I usually, like when I go to a museum, I see not always, but usually I see art that is a physical object.
Right.
Or has been expressed as such. So
Right.
there is,
Well,
for any such work, there is the transition from the abstract into the concrete.
Right.
thing.
I guess he was maybe talking more about the experience of the artist and the
Oh, I see.
experience of the scientist. In other words, you have to not just do it once, but like 100 times, and fail as you go, and so on and so forth. And that the artist can just sort of, keep making imaginary atoms. I don't know, whatever.
Yeah, my personal take on that, maybe it's kind of in a different direction, but so dealing with atoms, like atoms are fairly abstract. Like I can't, yes, I know they exist, and yes, I've seen them in like an electron microscope, but like they're at some level they're intangible, and it almost seems like I'm dealing with. I have evidence that this imaginary world of atoms like does actually exist, and so making models or making things where I can get feedback. I mean, like one of the issues with these quantum mechanical calculations is that they take so long. You want to change one thing, and you have to wait 3 days for your calculation to come back. So I'm really excited about the possibility of actually getting design tools that have the quantum mechanics built into it, but I can actually interact with it like I would something at the human scale. And so actually, I do need sort of an analogy. I need to sort of push it around in a way that isn't really authentic to the physics, the atomic physics, but allows me to draw those analogies with my human experience so that I can then propose different ways of putting them together.
So the physical model is like a metaphor for what's really going on at the atomic scale.
Yeah.
That's
Interesting.
That's interesting.
That's flipping it around from what I was thinking, that like the idea in your head is the metaphor, and then you express it with something concrete.
Yeah.
That's almost the reverse.
Yeah. So that's why I think tools are like just so invaluable. Because I mean, a tool and a model, I mean, the terms are synonymous, because whether or not it's like literally like a hammer versus an equation on a board, those are the analogies, or those are how we transform our kind of limited human capabilities into handling the world around us, whether it be quantum physics or the fact that I can't bend sheet metal with my hands, so, much as I try.
Got to start working out.
Yeah, I know.
It helps if you score.
Yeah, that does make it better. So
I think this is a good moment to open up to audience questions, but I just want to just say it's so obvious in your presentations and just who you are that you just really have a great time doing what you do. It's like so fun for you, and that's just a great thing to, be doing serious work but like having fun at the same time. It's great.
Yeah, I forgot to mention having fun is like the primary motivator
Yeah.
for everything that I do.
Yeah,
So
it's cool.
yeah.
it's been
Yeah.
oh, that would be useful, but this would be fun.
And then you can write a
Sometimes they
paper.
overlap, but
Yeah.